Hey folks, Ms. Gosling here. In this video, you're going to learn more about the anatomy of a wave. By the end of the video, you'll be able to describe the relationship between simple harmonic motion and waves, and, more importantly, label the parts of a wave. So let's go ahead and get started by looking at transverse waves. So we define a transverse wave as a wave where the direction of propagation, which I'm going to call V, so the direction that the wave is moving in, is perpendicular to the displacement of the wavefronts, to that motion of my wave. So our transverse wave has a few important parts to its anatomy. The first thing is the wavelength, and that is the time to go through, is the length of one full cycle. So for example, if I start at a peak, my wavelength is how long it takes me to go through one full cycle back to my peak. And I'm going to use the character lambda to recognize my wavelength. Now you'll notice that I mentioned the word peak. So the peak of a wavelength is going to be the highest point. So these are both peaks. Similarly, the lowest point on a wavelength we're going to call, or on a wave, we're going to call a trough. So peaks and troughs. Now the amplitude of the wave is going to be the distance from our equilibrium to either a peak or a trough, because our peaks and our troughs are the same distance away from our equilibrium. So that is our amplitude A. Now, the last thing that I want to mention is something that's a little bit hard to see here, but just like an object in simple harmonic motion, a wave has a period, which is the time it takes to go through one full cycle. So at this point, we're assuming that our graph is showing displacement over distance, so how far different points are going up or down. We could also be showing displacement over time, so looking at a single point in space and seeing how that point in the wave is changing over time. And if that were the case, the period would be the time it takes to get through one full cycle, or the time it takes to go through one full wavelength. And just like in simple harmonic motion, the period is equal to 1 over the frequency, which we're going to measure in hertz. So that is our transverse wave. Now I'd like to talk about longitudinal waves. So a longitudinal wave is a wave where the velocity of the wavefronts, so the direction of wave propagation, is parallel to the direction that the wave is kind of waving in, the way that where its compressions are, where its areas of highest and lowest energy are. So a good example of a longitudinal wave is actually a sound wave, because sound waves are created, they're a kind of pressure wave, and essentially what happens is you put out a sound, and that's going to cause air molecules to vibrate against one another in the same direction that you're speaking in. So just like a transverse wave, a longitudinal wave has a wavelength lambda, and that's going to be the distance, the length for one full wavelength. So here, this is kind of approximately lambda. It's a little harder to see on a longitudinal wave. Now, instead of crests and troughs, longitudinal waves have compressions, where the wave is closer together, and that motion is closer together, and rarefactions. And note it's rarefaction, not refraction. Rarefaction. And that's the areas where there's more space between wavefronts. It's that kind of wider part. So think about when you bounce a slinky around, where the slinky is close together, we've got a compression. Where it's far apart, we've got a rarefaction. Now, just like we can talk about wavelength and period for a transverse wave, we can also talk about wavelength and period for a longitudinal wave. Again, assuming that we're looking at a point in time, the change in a point in time in the wave in a point in time versus the change in the wave over a point in space. And for our longitudinal wave, our period, again, is still related to 1 over frequency, just like it is for a transverse wave and for simple harmonic motion. So before I take us to takeaways, I do just really carefully and clearly want to go over that relationship between period and frequency, because this is something that's going to be really fundamental to our unit going forward. And again, the relationship is that our period is equal to 1 over our frequency. And more specific, and we can kind of see that relationship in the definition of period and frequency. So our period is the time for one full cycle, and we're going to measure that in seconds. Our frequency is how many cycles happen in a second. So you can see that that is really exactly 1 over our frequency, right? Or our period, because our period is time over cycles, and our frequency is cycles over time. And we are going to be measuring our frequency in hertz, which is going to be shortened as Hz. So I just really clearly and carefully wanted to go over this because I think that this is something, or because I know that this is something you will be using a lot in the future. And I just want to make sure that you guys are very clear in your understanding of that relationship between period and frequency, as well as going through those units again with you one last time. So now we're ready for takeaways. So like simple harmonic motion, waves are periodic. They have a period, they have a frequency. However, unlike simple harmonic motion, we are seeing things traveling through space instead of returning to an equilibrium position. So we see an equilibrium position within the wave, but the wave itself now has a horizontal velocity, or vertical velocity really. It's just moving through space in a direction as well. So it's not staying in that same spot. And then finally, waves have many different parts. It's important to know those parts. They're different for transverse and longitudinal waves. And that's really all I have for you. So I'm going to go ahead and let you continue on, learn a little more about how traveling waves behave. Best of luck and happy learning.